this hidden layer. And we'll talk about deep learning later on in the course. But deep learning is simply the, from a high level, simple sort of explanation. Deep learning is simply the generalization of what I just described to many layers, right? Not just two, maybe 200. Right? Why might one prefer a deep network over a quote-unquote fat two-layer network? Well, one reason is compactness, right? Just like when we talk about things that are in circuit complexity, sort of in Boolean circuits, you know that the modeling power of a Boolean circuit increases with the depth of the circuit, right? Similarly, you can make similar you have similar ways of reasoning about the modeling power of a neural network as you increase the depth of, or the number of layers, rather than making a relatively shallow network relatively fat. Sometimes these really deep networks are actually easier to train than the really fat, shallow networks, and this is something that may come up in a future homework. Yeah, we'll discuss this further in the future, just as an aside. Training deep neural networks typically use gradient descent or stochastic. By the way, whenever I say gradient descent, from now on, I always mean stochastic gradient descent. You could write out the functional form of the y's as this, right? And then you could derive out the gradients. It's just basically chain rule. I won't make you sort of read this, in detail. It's just chain rule. In the computational neuroscience literature, they call this back propagation. It's just gradient descent, stochastic gradient descent with chain rule. And the chain rule is required because the gradient on the weight corresponding to this arrow requires propagating up the network. So we'll get into this in greater detail in future lectures. Just wanted to sort of highlight this and how it connects to what we've been talking about so far. Okay, so the final part of the lecture, I wanted to briefly talk about different evaluation metrics beyond accuracy, beyond 0-1 loss, that you may find useful as you leave this course and you try to use machine learning in many real-world scenarios. Right? So we looked at two ways of quantifying the performance of a model during evaluation, right? 0-1 loss and for classification, and square loss for regression. And I'll talk about a few others now. Right. Here's an example. Suppose we train a machine learning algorithm to predict cancer given some inputs, right? So we have what the model predicts and then some notion of the truth, right? And so at a high level, we want a loss function when we train this model to have the following properties, right? If the patient actually has cancer and we predict cancer, the loss should be low, maybe 0, right? If the patient does not have cancer and we predict cancer, okay, that kind of sucks, right? But it's not the end of the world, right? If the patient has cancer and the model predicts no cancer, that is awful, right? It's like well, both of these are lawsuit worthy, but this one's really lawsuit worthy, right? In some sense, or really high loss. And then if the patient does not have cancer and the model predicts cancer, the loss should be low, right? So the key takeaway of this is that we value positive and negative examples differently, right? Positive examples, for examples that are actually that have a positive label, if we mispredict, we pay a large penalty. For examples that have a negative label, if we mispredict, we pay a lower penalty. Right? This is typically formulated as a quote-unquote cost matrix, and 0-1 loss is a special case where it's symmetric, or I guess in this case anti-symmetric. Right? Or I know it is symmetric too. Yeah, it's symmetric. And so here is one way to sort of formulate this loss function, right? So there's no universally accepted way. This is just one way that I sort of propose for this simple problem, right? So the loss of predicting cancer when the patient does not have cancer. So if the label is -1, we predict +1, the loss is 1. If the label is +1 and the model predicts -1, the loss is 1,000. In the case of simple 0-1 accuracy, the loss is 1 and 1. Right? So it's skew symmetric. The cost matrix is skew symmetric. I think that's the right term. Anyways, you get my point. And so the way you would sort of write it out mathematically, something just looks like this, right? So for you sum over labels that have +1, and you have sum over labels that have -1, whatever surrogate loss function you choose, so hinge loss, log loss, whatever, you multiply the ones with positive labels by 1,000. Okay. Any questions on that? Okay, so in many cases, when we think about using machine learning algorithms, we think of using machine learning within we think about the predictor we train using machine learning within a pipeline of some other process, right? So we have a bunch of examples, we predict the ones that we think we use machine to predict the ones that we think are interesting, and then we take those examples and we do something else with it, right? So what we really care about is making sure that whatever the machine learning says is interesting is actually interesting, right? Mathematically, or more formally, you can think of that as thinking about if the model predicts positive, is it actually a positive example, right? And so there are two ways, or three, I guess, in this slide to quantify that. The two simpler ones are called precision and recall. So in this matrix, if you predict positive and the ground truth is positive, it's called a true positive because the model predicted positive, it's actually true. If the model predicted positive and the truth is, and in reality the example does not have a positive label, it's called a false positive. If the model predicts negative, but in reality it's a positive example, it's a false negative. If the model predicts negative and in reality the example has a negative label, it's called true negative. It's the terminology. Precision is the ratio between true positive divided by true positive plus false positive. So it's the ratio between this number, 20, and the sum of these two numbers, 20 and 30. So of all the ones that the model has predicted as positive, what fraction are actually positive? That's called precision, right? So in this case, the precision is 40%. Okay. Recall is the fraction of true positive divided by the sum of true positive plus false negative. So if all the examples that actually are positive have a positive label, what fraction did our model predict as positive? If in the end we're only going to look at the examples that the model has predicted as positive for some downstream application, then these are the numbers that we care about. We don't actually care about true negatives, right? We care about precision, like if the model predicts positive, am I wasting my time looking at this example? And we care about recall. Did I make sure that I actually have coverage of all the true positive actual positive examples? F1 score is simply the harmonic mean between precision and recall. So in all these cases, we care much more about the positive examples than the negative examples, right? Here you notice that we have a class imbalance, right? There are 25 examples that are positive and 100 examples that are negative, right? So the more interesting things are the positive examples. We really care about getting them but we want our model predictor to be pure and not predict a lot of negative examples on the way to predicting all the positive examples, right? These types of applications, these types of measures are useful for lots of things. So here, so for example, so like if someone has cancer, if the model predicts someone has cancer, there's something you do downstream, like you do a biopsy, right? And if the person actually does not have cancer, then you pay the cost here, right? If you predict no cancer, assuming you trust this model with some reliability, then you don't do anything, right? Yes?
What does F1 mean between for example?
Why are we taking a harmonic mean? Imagine if precision was if we predict, here's a thought experiment. Suppose our model is predicting everything as 100, everything is positive. So there's nothing in these two columns, everything is in these two columns, right? What is the recall? There's nothing in these two rows, everything's in these two rows, right?
So the recall is more.
The recall is 100%, right? And the precision is some low number, right? It's not a very useful model. Under the harmonic mean, I'm doing this, I'm remembering this in real time, but I'm pretty sure that if either precision or recall is 0, the harmonic F1 score is 0.
Yes.
The model is useless if either precision or recall is 0. Yeah. If you do the arithmetic mean, you don't get that. Okay, so here's another example that's very similar. Suppose we issued a search query and some search engine is ranking the web pages by relevance, right? And suppose I have a bunch of search results in some 2D feature representation here, and these are the two relevant examples. And every other search result is irrelevant. So here's what often happens in practice. Let's suppose for simplicity that users only look at the top 4 results, and then they sort of, ignore the rest, right? So issue some query, you search for the query, and you issue the results for the query. Then this is sorted by the confidence, some notion of confidence in the probability. Let's say that the relevance of this query is that this result of this query is relevant, right? So here's the top 4, and let's suppose for simplicity that there are only 6 results, and these are the 4 that we predict as rank as the top 4. And the first one is relevant, the fourth one is relevant, the last one is relevant, right? Then we could define a measure called precision at 4, right? If we're not just predicting positive or negative, but we're just predicting a ranking, right? So we use this model score to predict a ranking, and then often what happens is, I'm going to rank something, and I only have time to look at the top 4 for downstream processing. I only have time to look at the top 10 for downstream processing, right? So precision at 4 says only look at the top 4 results in the prediction sorted by the model score, and measure the fraction that are relevant. And in this case, it's 50%. Recall at 4 says, okay, look at the results in the top 4. How many of them did I get? How many of the relevant results did I get versus the total number of relevant results? There are 3 relevant results, 2 of which are in the top 4. So the recall at 4 is 2/3. So, yes?
For an application like this, how would you know what's relevant or not?
You assume it's labeled. So for example, what Google does is they have humans say, for this query, this web search result is relevant, yes or no. There are other ways to do it, but that's sort of the standard. You could also do pairwise preferences. You could also measure rankings by pairwise preferences. Suppose this is sort of the model score. It goes in this direction in this feature space. So that this would be the first rank result, second rank result, third rank result, right? Then you can look at pairs of documents pairs of search results between relevant and non-relevant results. Here we have a non-relevant result ranked above a relevant result. That's a pairwise disagreement. Here we have a relevant result ranked above a non-relevant result. That's a pairwise agreement. You sum over all pairwise agreements and disagreements. There are 2 pairwise disagreements, this guy and this guy versus this guy, and 4 pairwise agreements, these 4 versus this guy. And that's a way of measuring the quality of a ranking as well. And that's what you use to compute a measure called the ROC area, which some of you I'm sure have already seen so far in some other context. And the ROC curve is basically a curve of the false positive rate versus the true positive rate. So if you have a model that scores all the examples, and you rank them by that score, and then you have some actually positive examples and actual negative examples, the ROC area, so the area under this false positive rate, false negative rate curve, is the fraction of pairwise agreements over all possible pairwise agreements and disagreements. So here's an example. If I had a ranking like this, where we have from the top of the ranking to the bottom ranking, positive, negative, positive, negative, positive, negative example, there are 6 pairwise preferences. So there's two negatives, all possible positive, negative example pairs. So there's 6 of them, 3 times 2. And the number of agreements is 3. So the ROC area is 0.5, which is actually very bad because it's like it's no better than randomly sorting the examples. Average precision is another ranking measure. I think this is the last thing we'll talk about today. And it's the area under the precision recall curve, right? So as we sort of increase the rank of our, so if we rank all the items by our model score, and we go down the ranking, say we're only gonna look at the top 5, top 6, top 10, whatever, when we measure the precision and recall of each of those, at each of these rank cutoffs, you get these types of curves, because as you sort of decrease the rank, the recall goes to 100%, because in the end you're looking at everything, which must necessarily include all the positives, but your precision goes down, right? So for our average precision, you compute the precision for each positive location, each positive entry in your ranking, and then you average them. That's what average precision means. So in this particular ranking, you get a rank. You compute the precision at rank 1, precision at rank 3, and precision at rank 5, and you average them. You get an average precision of about 0.76. So this is the last comparison. How do we think about these different types of measures? The ranking measures ROC error versus average precision. ROC error cares about every pairwise preference equally. Average precision, if you actually work out the math, cares more about the top of the ranking, right? So if we look at this ranking, you get an average ROC error of 0.5 if you work out the math, and you get an average precision of about 0.76, and that's weighted by the fact that you're averaging something that's actually a 1 here, right? You look at this ranking, where the top result is negative, and you get again an ROC error of 0.5, because it cares about all possible pairs of misrankings between all pairs of positive and negative examples, but the average precision is lower, right? So average precision is more top-heavy than ROC error is. So when you think about, okay, I'm using machine learning to actually produce a ranking of items, and I only have time to look at the top 10. What objective function, what evaluation measures should I use to evaluate the quality of my machine learning algorithm? And then these are some of the things you should think about when choosing your evaluation measure. Just to summarize, there are actually many other different evaluation measures beyond accuracy and sort of squared loss regression error. The ones I talked about at the end of this talk, end of this lecture, are largely focused on the case where you really care about the positive examples and you have some potentially some finite budget, and it's part of some downstream application. And there's often a class imbalance because the positive examples are very much rarer than the negative examples. Right? And potentially, a large cost of mispredicting the positive examples as well. Any questions on that? Yes?
So for all of these measures, if you want to optimize for them and design your own loss functions, so how do you integrate that with an SVM or something?
Right. So the question is, how do I actually? Are there learning algorithms that actually optimize for these loss functions? Right. So here I'm just talking about evaluation, right? And the answer is yes. There are learning algorithms that optimize these loss functions. There are generalizations of support vector machines that optimize for all these loss functions. Yeah. So the next lecture, we're going to spend the entire lecture on regularizations and last one, which is a type of regularization. Tonight, linear algebra recitation.